So, hey, here's some outliers. They show up on the residual plot by being all very high instead of these here, which are all kind of scattered around the regression line. Note, though, that they affect the slope of the regression line here, which again you can see from the residual plot in that here we've got mostly positive residuals and here we've got mostly negative residuals. And that's because these outliers are pulling the residual line up towards them, which means that we then are overestimating for this end down here. So, right, think about what the regression line would be without the outliers. If we were to ignore those outliers and draw a regression line, it would probably go more like this. So these outliers are pulling up that bottom end of the regression line, giving us a flatter slope. So without the outliers, the regression line would be steeper and be closer to the rest of the observations. What about this one? How do outliers influence the least squares line on this plot? This is an outlier. Without the outlier, there's no evident relationship between x and y. If we take this outlier out and we just look at this data, we're going to get a slope of 0 here. There's no positive relationship. So this one outlier is the only thing really giving us a positive relationship. So outliers are points that lie away from all of the other points. Outliers that lie horizontally away from the center of the cloud are called high leverage points. The high leverage points are going to affect the slope. And they're called high leverage points that do actually influence the slope are called influential points. In order to determine if a point is influential, visualize the regression line with and without the point. Does the slope of the line change considerably? If so, the point is influential. If not, then it's not an influential point. So, consider. So, here's an LSRL. Here's some points. Here's an outlier. Right? This is a high leverage point because it is far away from the other points horizontally. But it is not an influential point because if I take this point out, the slope is still the same. It's not going to change the slope of the LSRL. Whereas if I have these points and then I've got this point, that is going to change the slope of my LSRL. This is a high leverage point because, again, it's very far away horizontally, but it's also influential because it changed the slope. Without this point, the slope would be like this. So here, right, here's some data on the log of the surface temperature and log of the light intensity of 47 stars in the star cluster CYGOB1. The log is one way that we can transform nonlinear data into linear data. So with the outliers, we get a weak negative slope. If we take these 4 outliers out, we get a fairly strong positive slope. So these outliers are high leverage points because they're far away horizontally, and they're also influential points because they are vastly changing the slope of the LSRL. So, does this outlier influence the slope of the regression line? Not really. right? This is not a high leverage point because it's in the middle. So whether it's close or far away from the line is not going to affect the slope of the line. And so it cannot be an influential point. So it is neither high leverage nor influential. Still an outlier because it's far away from the rest of the data, but it's not going to influence your LSRL. It will influence your correlation coefficient, though. So which of the following is true? None of these. Influential points do not always change the intercept of the regression line. They change the slope, not the intercept. Influential points do not always reduce your R squared. Low level points and high leverage points. High leverage points are more likely to be influential. Low leverage points will not be influential. Low leverage points would be more towards the middle of the data. When the data set includes an influential point, the relationship between the explanatory variable and the response variable is always nonlinear. Again, not necessarily. You may have a linear relationship with just that one outlier. So, none of these things are true. In 1966, Cyril Burt published a paper called The Genetic Determination of Differences in Intelligence, a study of monozygotic twins reared apart. This consists of IQ scores for what we're assuming is a random sample of 27 identical pairs of identical twins, one raised by foster parents, the other by biological parents. So the biological twins' IQ and the kid raised by foster parents' IQ. And got an R of 0.882, which is pretty good. And so this is the computer output for that. So we have the intercept and the slope, and we get the R squared value. Don't worry about the rest of that. This is the important bit for right now. So the slope for every additional point, every additional point increase in the biological twins' IQ, we get approximately, our model predicts approximately 0.9 points increase in the foster twins' IQ. Or we could say 10 points in the biological twins' IQ is associated with 9 points increase in the foster twins' IQ on average. So, right, 1 point and 0.9 or 10 and 9. Just multiply by 10. The R squared of 0.78 would be that approximately 78% of the variation in the foster twins' IQ is predicted by the variation in the biological twins' IQ. Does not say that the foster twins' IQs can be accurately predicted. The model here for the foster twins predicted, right? Foster twins IQ predicted is going to be the intercept 9.2 plus 0.9 times the biological twins IQ. And foster twins with IQs higher than average tend to have biological twins with higher than average IQs as well. That's also true. So actually all of these are true. This is which of the following is false. So B would be the one that's false. A, C, and D are true, right? This just means there's a positive linear relationship. Foster twins with higher IQs tend to have biological twins with higher IQs. Positive relationship. So B is the one that's false. We have the percent college educated versus percent Hispanic in LA. The relationship between the percent of college graduates and percent Hispanic in a sample of 100 zip codes in LA appears to be negative, linear, strong correlation. So I would say that this correlation is linear, negative, and strong. This is a pretty strong correlation here. Right? So here is the computer output, and so the slope is negative 0.75. So a 1 percentage point increase in the explanatory variable, the percent Hispanic, is associated with a 0.75 percentage point decrease. Not 75% decrease, a 0.75 percentage point decrease. This is B. It does not say that it decreases the percent of college graduates because that implies causation, which is not what we have. All right, and that's it for Outliers.